So if you're anything like me, you're always wanting more from your electronics, right? Faster phones, smarter watches, definitely more powerful computers for work, for gaming, you name it. But this constant push, this demand for better performance, well, it applies everywhere, from the phone in your pocket to those huge data centers powering everything.
Right. And it creates this enormous energy drain. It really does.
Exactly. So the big question is, what if we could, slash that energy use, radically cut it, even without losing the performance we want?
That is the critical question. Because as our devices get more complex, the need for advanced, super efficient memory systems just keeps growing.
It's escalating.
Yeah, it really is. And the current technologies, well, they're impressive, no doubt, but they are rapidly hitting their limits, especially on power consumption.
Oh,
It's a genuine bottleneck, slowing things down, driving up energy costs. It's a big deal.
And that's exactly what we're diving into today. We're looking at this, quiet revolution happening in materials science, something that could potentially save a massive amount of energy in, practically every gadget you own.
It sounds promising.
It really does. It's all thanks to a major breakthrough from University of Minnesota researchers. They've developed this powerful new alloy. It's called Ni4W.
Ni4W, okay.
Yeah, and their findings, already published in a top peer-reviewed journal, Advanced Materials. Plus, the team's already secured a patent for it.
Wow, so they're moving fast.
Seems like it. Okay, so our mission for this deep dive. Let's unpack this thing. Ni4W, what is it? How does it actually work? And why could it be such a game changer for, almost every electronic device you use?
Sounds good. Let's get into it.
So before we dig right into Ni4W itself, let's just really underline the problem again, this energy challenge.
Right.
Because our digital world keeps expanding, right? And it's not just bigger screens or faster downloads. It's this incredible hunger for energy that grows alongside it.
Absolutely.
We're talking, storing a simple photo on your phone all the way up to these giant server farms processing billions of searches.
Every single second.
Yeah. It all comes down to data storage and processing, and it's just incredibly power hungry. Sometimes I try to picture the energy a single data center uses. It's like imagining a small city's worth of electricity. It's truly staggering when you think about it.
It absolutely is.
Yeah.
And look, this isn't just some abstract issue. It's a very real challenge and is driving intense research all over the world.
Right.
Scientists are actively looking for new materials, things that can either seriously boost current memory tech or maybe replace it entirely.
Okay.
And the main goal is crystal clear. Achieve a massive cut in power use, but without sacrificing performance or speed. That's the tricky part.
And that search, that relentless hunt for a solution, is exactly what led these University of Minnesota researchers to this alloy Ni4W, which you said is unique. It's made just by combining nickel and tungsten, two pretty common elements. But what makes it special, you mentioned, is its low symmetry structure. Now, why is that detail so important? Can you break that down a bit?
Absolutely.
Yeah.
That low symmetry structure,
Yeah.
it isn't just a minor detail. It's really the secret sauce here.
Okay.
See, in many materials, atoms are arranged really neatly, symmetrically. But in Ni4W, the arrangement is a bit lopsided, off-kilter, low symmetry.
Got it.
And that unique structure is what allows it to generate something called strong spin-orbit torque. We call it SOT for short.
So SOT, spin-orbit torque.
Right. And you can think of SOT as like a very precise, very tiny little kick given to a microscopic magnet.
A kick?
Yeah, allowing it to flip its state, its magnetic direction, with incredible efficiency, using minimal energy.
Wow.
And this is crucial because that flipping action, that's a fundamental way we control magnetism in these advanced cutting-edge memory and logic devices.
Okay, that sounds like a monumental step then. So Ni4W can deliver this tiny, efficient kick, this SOT. But here's where you said it gets really interesting. It can switch these magnetic states without needing external magnets.
That's the key innovation.
So, for us listening, what does field-free actually mean in practical terms? Like for the size or efficiency of a device?
That's a fantastic question. It's hugely practical. Normally, right, to switch these tiny magnetic states, you'd need a separate magnetic field.
Okay.
Often generated by little coils or other components that, frankly, use quite a bit of power and take up valuable space on the chip.
Right. Adding bulk and draining power.
Exactly. The amazing thing about Ni4W is that it eliminates that entire need. It performs the switch just by passing an electric current directly through itself. No external magnetic field needed to influence it, this field-free switching ability. That's the major differentiator.
I see.
Yufei Yang, who's a fifth-year PhD student and one of the co-first authors on the paper, explained it well. He said, unlike conventional materials, Ni4W can generate spin currents in multiple directions, enabling field-free switching without the need for external magnetic fields.
Okay, hold on. So if I'm getting this right, it basically gets rid of a whole separate component, a power-hungry one that used to be essential for this type of memory.
You got it. That's what field-free really means here.
Wow. And what about these spin currents you mentioned?
Good question. So it's a Ni4W integrates the field generator right into the material itself, saves huge amounts of energy and space.
Okay.
Now, spin currents, they're not just your regular flow of electrons like electricity in a wire. They involve controlling the electron's intrinsic magnetic property, their spin.
Ah, okay, it's about their magnetism too.
Precisely. So instead of just pushing electrons along, we're also harnessing and directing their tiny magnetic orientations.
Fascinating.
And Yufei Yang also noted, we observed high SOT efficiency with multi-direction in Ni4W, both by itself and when layered with tungsten. This, he says, points to its strong potential for use in low-power, high-speed spintronic devices.
And multi-direct.
Yes. That ability to generate these spin currents effectively in multiple directions, that's the real innovative leap here. It makes the field-free switching super effective and efficient.
So it's a fundamental shift away from how we normally do electronics.
It really is. It opens the door to incredibly efficient devices, these spintronic devices.
The implications here just feel immense, especially when you circle back to energy reduction across the board.
Yep.
We're talking about devices doing basically the same job, maybe even better, but using just a fraction of the power. What sort of scale of energy savings are we potentially looking at?
Well, potentially very significant savings. Jianping Wang, he's a senior author on the paper, a distinguished McKnight professor.
Right.
He put it quite directly. He said, Ni4W reduces power usage for writing data, potentially cutting energy use in electronics significantly.
Significantly, that's the key word.
It is. And if you connect that to the bigger picture, well, this kind of breakthrough is vital for lowering electricity demand everywhere. It points towards a future with much more efficient tech, much more environmentally friendly tech, reducing the energy footprint of everything.
Yeah.
From your phone right up to those massive data centers.
So the applications could be incredibly wide-ranging then.
Absolutely.
You're talking everything from the tiniest devices we wear, like smart watches, fitness trackers, up through your smartphone, your laptop, and then scaling all the way up to those enormous data centers processing just unbelievable amounts of information.
Exactly. The potential reach is vast.
So this promises not just, faster, smarter computer memory, but it also really opens the door for these genuinely low-power, high-speed spintronic devices you mentioned.
That's right. And this brings us to another really practical, really important advantage of Ni4W.
Oh, what's that?
It's made from common, abundant metals. Nickel and tungsten. We're not talking rare earths or anything exotic.
Okay, that's good news.
And crucially, it can be manufactured using standard industrial processes, the kinds already used in chip fabrication.
Ah, so no need to reinvent the entire manufacturing wheel.
Precisely. This makes it a potentially low-cost material, which is obviously a huge deal.
Yeah, absolutely.
As the team pointed out, this characteristic makes it very attractive to industry partners. Why? Because it could allow for quick, broad implementation into the technology we rely on every single day.
So it's not just scientifically interesting, it's actually practical for scaling up.
Very much so. It's something that can realistically be scaled for mass production.
And we should stress, this isn't just some pie-in-the-sky idea. It's backed by really rigorous research.
Absolutely.
Published, as we said, in Advanced Materials back on May 15th, 2025. And the University of Minnesota team has the patent locked down. How did they actually validate these findings? What was the process? And what's next for them?
Well, the scientific rigor is pretty clear from how they approached it. They combined theoretical calculations with hands-on experimental observation.
Okay, theory and practice together.
Yes. And Seongjun Lee, who's a postdoctoral fellow and the other co-first author, confirmed this. He said, "We are very excited to see that our calculations confirmed the choice of the material and the SOT experimental observation."
So the math checked out and the experiments proved it worked.
Exactly. It's not just a simulation, it's proven in the lab, which gives everyone huge confidence for its potential future applications.
Makes sense.
And This work wasn't done in isolation. It was a truly collaborative effort, a large team of really brilliant people
Right.
from across different departments at the University of Minnesota, electrical and computer engineering, chemical engineering, and material science, with key senior leadership from professors like Tony Lowe.
It takes a village, as they say.
It really does. And it's also crucial to mention the support they received from organizations like SMART, Encore, and the Global Research Collaboration Logic and Memory Program. These initiatives are vital for pushing this kind of research forward.
Absolutely. So what are the next steps for the research team then? Where do they go from here?
The immediate next steps involve continuing to grow these Ni4W materials, but aiming to integrate them into devices that are even smaller than what they've already demonstrated.
Pushing the limits of miniaturization even further.
Exactly. Seeing how well they can go while maintaining this high performance and low power.
Okay. So if you're taking away just one thing from our deep dive today, it really feels like it's this. Ni4W isn't just, another material discovery.
No, it's more fundamental.
Yeah, it seems to represent a potential fundamental shift in how we might design and power our electronics in the future. It offers this clear path towards significantly more efficient and, importantly, more environmentally friendly technology. It really could be a game changer.
Absolutely. So, thinking about what this all means for you listening right now.
Yeah.
Well, innovations like Ni4W, especially because they're made from common stuff and fit into existing manufacturing, that could directly translate into real benefits you'd actually notice.
Like what?
Well, think about longer battery life for your phone, your watch, your laptop. That's a big one for most people.
Definitely.
Also, a really substantial reduction in the energy guzzled by those massive data centers that basically run our entire digital world.
Right, the invisible energy cost.
Exactly. And ultimately, that means a much smaller environmental footprint for technology overall. It's about making your tech work better and be greener, using materials that are actually readily available.
It really makes you wonder, doesn't it? I mean, if a relatively simple alloy, like Ni4W, just nickel and tungsten, these abundant elements, if that can fundamentally change how devices store and process information, potentially leading to these massive energy savings, what other invisible breakthroughs are happening right now in materials science, things we don't see quietly being developed, that could reshape our future in ways we can barely even imagine, making our world not just smarter, but, profoundly more sustainable?
It's an exciting thought. The potential hidden in basic material science is often overlooked, but it could be absolutely transformative.